start this whole day over. Okay, we're going to talk about testing hypotheses about proportions today. So this process is really similar to the one that we had before. The only difference is that when you calculate the standard deviation of P1 hat minus P2 hat, you use this formula because we're talking about two different proportions. And I don't know, but I think the numbers on your sheets got a bit off. And this might say example 8.
Yeah.
I fixed it, but it's because I broke something that was one sheet into two sheets. So one question that we're going to talk about for this example is the proportion of men who write a shopping list before grocery shopping or going shopping less than the proportion of women who do so? Personal experience, my dad refuses to make lists and it makes me crazy because he then has to run to Home Depot 3 times, and when this happened I kind of got frustrated and he was like, I don't need to make a list, I've got it all in here. I'm like, yeah, you just disproved your hypothesis. Okay, moving on. So we're going to let P1 and P2 represent the population proportions of men and women who use shopping lists. And suppose that we have a sample of 50 men and 50 women, and they were asked if they use shopping lists when they have more than 10 items to buy. Of the 50 men, 20 said yes, and of the 50 women, 30 said yes. So we're going to show all 5 steps in hypothesis testing. So the question is are these proportions the same, or do men make lists less often than women? That's kind of the thing. So the first thing is state the null hypothesis and alternative. So the null hypothesis is that men and women make the same amount of shopping lists, right? That would be P1 equals P2, which translates into P1 minus P2 equals 0, right? Okay. HA is that women make shopping lists more. So how do P1 and P2 relate to each other then? P1 is less than P2, or P1 minus P2 is less than 0, right? That makes sense? Okay. So that's always your first step. If the question doesn't ask you, like it does, if the question doesn't give you the steps in A, B, C, D format, please label them step 1, 2, 3 to make your grader's life a teensy bit easier. I think I try to save that in the notes, but try to label it step 1, null hypothesis. Step 2 is to summarize these data into an appropriate test statistic after verifying the necessary data conditions are met. So the data conditions that have to be met are these quantities, NP1, N1 minus P1, NP2, and 1 minus P2 all have to be bigger than 10, yep.
Or 10.
Or 10, yep, bigger than or equal to 10. And the tricky thing about this particular procedure is that IDK, what's the null value? Do you see what I mean by that? If those proportions are equal, what should that equal proportion be? Does that make sense? And that's trickier here. So here is how you find it. The first thing to do for anything is to find the null value. So if P1 equals P2, what value is this?
0.
Not necessarily, because those two things could be equal by both being 0.5. Or they could be equal by both being 0.3. Does that make sense? And if your populations are different, if your samples are different sizes, it isn't necessarily a straight up average of the two. So what we're going to do for our null value here, so the formula to find it is, they call it P hat, and it's N1 times P1 hat plus N2 P2 hat over N1 plus N2.
Finding the average.
This is finding what's called a weighted average. Yep. And the weighting of the average means that somebody is more important or bigger group than somebody else. Okay. So, and to do that, holy moly, you need a lot of information. Like, you're going to need P1 hat. So what is P1 hat? 20 out of 50, which is 0.4, right? What is P2 hat? 30 out of 50, which is 0.6. So we do 50 times 0.4 plus 50 times 0.6 over 50 plus 50. I think this comes out to be 0.5. So in this case, notice how that was an average of those two values, but that's because the sample sizes are equal. Does that make sense? If these sample sizes had been unequal, then it wouldn't have been just this one plus this one divided by 2. That's a special case. This was an exception. Okay. Also, does this make sense that this is the same thing as 20 plus 30 out of 100? You could think it's the number of people who made lists, whether they're male or female, out of the total sample size. So either way. But the trickiest thing you have to do here is first find this alleged null value. And then you've got to use that to compute all these guys. But if your sample size is 50, these are each going to be 25. Does that make sense? So we're good to go. And I do apologize, this step B needs more space than I gave you, but the later steps don't need that much space, so you can bleed into them and it's not a problem, okay? See what I mean by that? You can go into part C on the side and you'll be fine.
We got plenty of space.
Okay, did I change it on your notes so there was, I think not so much, but I write big. Okay, so we found the p-hat. Now we have to find the test statistic. And the test statistic, that's that whole z-value thing. So the z-value is p1 hat minus p2 hat minus your null value divided by your standard error of your null value. Does that ring a bell? Do you see how that's kind of the same as last time?
Yeah.
Except for last time we just had one p, right? Okay. And the standard error of your null value is given by this, root p hat 1 minus p hat over n1 plus p hat 1 minus p hat over n2. Do you see how it's a teensy bit different than last time? It is, and that's because you assumed that P1 equals P2.
Okay.
Does that make sense?
Yeah.
Yep, do you guys understand her question? So on top of the paper, because you have this assumption that P1 and P2 are equal, you have to use this P hat thing that is that value where they would be equal.
You've always had the assumption.
You always have that assumption that they're equal because you're testing whether or not these things are different somehow. So that's always going to be the case that these end up being the same thing, which is definitely a little bit confusing. Okay, so let's find that in this case. So our p hat was 0.5, right? So that's 0.5, 1 minus 0.5. Our n1 is 50. And our n2 was also 50. So how about you get me a decimal for what that is?
0.005 for each.
.005 for each of them? Okay, so when you add them together and root them, I got 0.1 exactly. Did you guys get 0.1 exactly? Okay. All right, so now that we have all the information, I think we can actually find the z value. So what is P1 minus P2? Or sorry, P1 hat minus P2 hat.
Negative 0.2.
Yeah, that's 0.4 minus 0.6, right? What's the null value we have?
0.1. Or sorry, no.
Well, that's, oh my gosh, I'm just not on it today. I'm so sorry. The null value, let me back up for a moment. No, it's not actually that far. It's only one step. This null value needs to be 0.5 minus 0.5. Think about that for a second. Why is that the case?
0.5 is the median.
Yeah, and because for this one, this is a difference in two proportions, right? The second thing here is we assume those proportions are equal, right? Does that make sense?
So if we assume the proportions are equal, the null
This-
value is always going to be
It's always going to be 0, exactly.
So should we just take that away instead?
As in just say that this is 0?
Yeah.
You can always do that, but that's the point, is that you have these difference in proportions, right?
Yeah.
And then the difference where they're equal is your null value. That's why this is always going to be 0,
Okay.
okay? Not 0.5.
So we have to keep that in the equation though,
Well, I think your question is, can I just say that that's 0?
Yeah.
The answer is yes.
for any,
For anything that's
Situation.
difference in proportions, you can always say it's going to be 0.
okay.
Yep, because you're always testing, are these two things equal or not? And so this null value, in the case of differences, will always come out to be 0.
Okay.
And then what goes into your standard error of your null value?
0.1.
0.1. I think your z comes out to be -2. Okay. So part C says to do what?
P-value.
And so our null hypothesis was that P1 is less than P2, right? So we want the probability that our z value falls even lower, that it's less than or equal to -2. So is that one you can get from your z table?
Yeah.
Yeah, so how about you try to find it?
Screwed.
Get a z table. Those I know I have extras of someplace.
0.0228.
0.0228? Okay. So what that means is that if the proportion of men and women who make lists was actually equal, you're only going to see a sample difference like this with probability 0.0228, like one like this or more extreme. So is this result statistically significant? That depends a little bit, but what's the standard level of test? Okay, so is this result statistically significant? Yes. Since P, which is 0.0228, is less than 0.05. So yes, this is significant. And what does that lead you to conclude? Reject H naught. And write both like in statistical terminology, but then also write what it means in words in this particular problem.
Oh, you did the alternate, oh, never mind, sorry.
Yeah, reject H naught, accept HA, that's the same thing, right? Okay, so when you reject H naught, this means that what's true? And HA is that men do what?
Make shopping lists less.
Make shopping lists less often than women.
That's part E?
Yes. Make a conclusion in the context of the situation. only have one of those. I'm sorry. So let me just pause for a second and I want to. So statistical sample size, statistical significance, and practical importance. So when there's a small to moderate difference between the null value and the true population value, a small sample has little chance of providing statistically significant support for the alternative, and the power is going to be low. I think we talked about this with, this is what makes one thing with election predicting tricky, is that if the true proportion is like 0.52 who support a candidate, it can be really, really hard to conclude that more than half the people support that candidate because that's awfully close to 50-50. Does that idea make sense? Okay. With a large sample, even a small and unimportant difference might lead to a conclusion of statistical significance. I think I had an example of like eating cookies, that if you eat cookies, then their chances of cancer double. But your baseline risk of cancer was like really, really, really small, and doubling meant was like not a big deal. There was a study recently done about, it was about processed meats and cancer. Did you guys hear about this at all?
Yeah.
And they said, oh, eating meat is as bad for you as smoking. That was the conclusion of the study, okay? But if you read it, the baseline risk went up by like 1.2.
You also had to eat like 25 pounds of meat a day.
You had to eat a lot, whereas like with smoking, the incidence from one group to the next was like up 13 times. So this was actually an example of that kind of baseline risk maybe not meaning anything. Anyhow, somebody that I also like read something online from somebody who's a doctor and a like mathematician who wrote about this, and they're like, yeah, that was silly. They shouldn't have made that conclusion. So.
There's also multiple studies about how, like, for each slice of bacon you eat, it takes like 7 years off your life. Or then it's like, if you like.
I guess I'm dying young then.
All died like 40 years ago.
Yeah, I think that's an example of applying the linearity principle too far in the future. Wasn't there that example about we're all going to be super fat one day? Like we'll all be like Wall-E? That's the same principle, right? Yeah. Except for then and they were saying thing about childhood obesity like a little bit ago, but that has actually like leveled off and is now decreasing. The point is things don't usually continue indefinitely. Okay, suppose that in a taste test, 55% of the participants actually like drink A better than drink B. Think like drink A is Coke and drink B is Pepsi, something like that, where it's pretty close to half and half, and people have strong opinions, okay? Like I can see Dirk shaking his head right now, like I hate Coke.
There's no such thing as Pepsi.
Exactly. So compute the test statistic and the p-value if this is the sample size. So if n is 60, and once again here we're back in like single proportion world. So the standard error of p naught is root p naught 1 minus p naught. It does sound like peanut. Little peanut. In this case, what is your null value?
0.5.
Okay. So we have root 0.5, 1 minus 0.5 over n, which is 60. How about you calculate that and tell me what it comes out to be?
0.0645.
Yep, 0.064. I got 5.5.
Yeah.
It would be 4.6 if you rounded correctly, but it's okay. Does that make sense though? Okay. And then let's find the z statistic. So z is p hat minus p naught over the standard error of p naught. So what's our p hat proportion that we observed?
0.55.
0.55, yep, we observed those people that prefer drink A. Minus our P naught, which is over,
0.06455.
yep,
Were these same numbers used for one of the homework questions?
possibly.
Yeah, it is.
Okay.
This comes out to be 0.77. Do you guys agree with that?
So,
Yes.
Question. For some reason on my calculator, it won't let me just type it in straight like that. I have to do the subtraction first. Like, I don't know if my calculator's broken.
Some calculators just have funny PEMDAS requirements on them, like you've got the same problem. Is it a Casio?
Hey, let's calm down.
Let's you calm down.
Might be a cat.
It might be a Casio. I have found Casio's like sort of system for inputting stuff to be a little bit tricky, and I can't always. It takes some serious time for me to figure it out myself. I find that TI whatever's Texas Instruments to be much better. And no offense to Casio, but I've just found it to be harder. Yes.
Can you just combine the equation? Can you, instead of doing finding
Two
the
steps.
standard error first?
Yeah. Could you just put that in there?
Yeah.
As long as you're careful with parentheses, you could.
Okay.
Yep. So in this case, because our HA goes this way, we want the probability that Z is bigger than or equal to 0.77. Does that make sense? How do we find that in practicality with our Z table? What do we use?
Z is less than negative.
Since we're talking standard deviations, is this going to be, do you think it's going to be statistically significant? No. What do you get for this number, for the p-value? 2206. Okay, so there's the p-value. So would you reject H naught in this case or fail to reject it? Fail to reject. And the reason here is that if the true value of the population is 0.5, seeing a proportion, a sample that was 55% would not be all that unusual. Does that make sense? Okay. What if your sample was 960 though? What's going to change specifically? Standard error, yeah. It's going to be root 0.5. 1 minus 0.5 over 960. This is going to get a lot smaller. So calculate it and tell me what you get. 0.0. 161. Okay, great. And then your Z-score now is 0.55 minus 0.5 over 0.0161. I got 3.1. What'd you get?
3.125.
3.125. Okay.
3.10.
I used .016 instead of 161.
Oh, okay. I got, well, you said you got 3.10.
105.
So let's go with 3.11. It's okay, as long as you know, I need to be very specific with how I ask you to round, but let's do 3.11. So what's the probability that Z is bigger than or equal to 3.11? Same as probability Z is less than or equal to negative 3.11. And if we're talking standard deviations, that's going to be a little bitty number, right? 0009. Yeah, so in this case, what would you do about H naught?
Reject it.
You'd reject it. And you would conclude more people like drink A better.
So for the first one, we just didn't have enough information to make.
For the first, we didn't have enough information, yeah, to observe a difference. Yep. So a bigger sample size will allow you to observe smaller differences. Does that make sense? Because 55% preferring a drink is not a lot more than 50% preferring that drink, right? The same as 55% of people preferring one candidate isn't that more than 50% preferring a candidate. Do you see what I'm saying? Yeah. So observing a difference that's kind of close to the null value will require, like saying that that's different will require a large population to establish that that's true. Which is what one thing that makes you can think about elections. One thing that makes predicting elections tricky because it's always close to 50-50, right? Look back at the past results, it's almost always half divided, so.
Somebody's not gonna be happy no matter what.
Pretty much, that's kind of the principle of democracy. So The phrase statistically significant means only that the data are strong enough to reject a null hypothesis. It doesn't actually mean that it has meaning in your world. So, for example, sometimes a result that is statistically significant doesn't have practical significance, which means this has very little meaning in your life. There's an example early in your textbook that says that the rate of air traffic controller mistakes doubled. And you're like, holy crap, I don't want to fly now, when they say this, right? But the thing is like the first rate was like something with a probability of like 0.000001. And then the new p had increased to 0.000000, like 3 or something like that. And air traffic controllers handle like a large volume of data, right? Which means that you're going to have a big sample size, which means that small differences in proportions could result in something that actually is statistically significant. Does that make sense?
Doesn't look like it is.
But doesn't actually look like it is, right? So this is much, much more likely to happen when the sample is very, very large.
Is that the same situation of the meat, or is that different?
The meat thing probably was different. The meat thing was the fact that the baseline risk didn't even increase all that much. Like it was a risk factor of 1.2
Okay.
versus like being 3 times higher or something like that. So large samples can detect small differences that might not have meaning. That's kind of the idea here. Large samples may find small differences that may not mean much. Okay. How about this next one? One possible problem is that researchers fail to find a statistically significant result, even though the null hypothesis is false. Okay, so even though H naught is false, you fail to reject it. That was a type 2 error, right? Yep, and that happens with a small sample. And that's because small samples will have relatively large standard errors, and as a result, it's hard to reject H naught in that case. So one way to decrease the chances you make that type 2 error where you fail to reject H naught is to make a bigger sample. Okay. Does everybody have a T table as well? Because we're going to move on to chapter 13.